Let's look at determining the required sample size when estimating the population mean mu. Suppose we are about to draw a sample from a normally distributed population where the population standard deviation sigma is known. We may wish to estimate the population mean mu to within an amount m with 95% confidence. The value of m would depend on the problem. We might wish to estimate mu within 1,000 or within 100 or within 0.00002. It simply depends on the setting. And the question here is, how large a sample size is required in order to estimate mu to within that amount m? Wanting to estimate mu within m is the same as wanting the margin of error to be no more than m. And here I've drawn in the 95% margin of error, and we need that to be less than or equal to this amount m. And now it's just a little algebra. We're going to move m down here, we're going to bring the square root of n up here, and then we're going to square both sides. And the result is this formula for the sample size that is required. This value 1.96 is the appropriate z value for a 95% confidence level. We can choose that confidence level to be anything we like. And to change the confidence level, we change the z value. So if we wish to estimate mu within some amount m with a confidence level of 1 minus alpha times 100%, we simply replace the 1.96 in the formula with the appropriate value of z. Let's look at a couple of examples. If we are sampling from a normally distributed population where the population standard deviation sigma is 65, how large a sample size is required if we wish to estimate mu within 4 with 95% confidence? Well, here's our sample size formula, and we want to estimate mu within 4, which means that our m is equal to 4. And the rest of these values we should know. Our n is greater than or equal to the appropriate z value for a 95% confidence interval is 1.96. Sigma is given as 65, and m is 4. And so we take those values and we square them, and we find out that n has to be bigger than or equal to 1014.422. Now, one point to note here, we need a sample size of at least this many, and n has to be a whole number, and so we must round up. And so the minimum sample size that is required is 1,015. What about if we wish to estimate mu within 4 with 99% confidence in the same setting? Well, again, we have our same formula, and n would have to be bigger than or equal to the z value for a 99% confidence interval is 2.576. We multiply that by sigma, which is given as 65, and m is 4 again. We square that, and we find that we need a sample size of at least 1,752.26 observations. But again, the sample size must be a whole number, and so we must round up and say that we would need at least 1,753 observations. Note that the required sample size to estimate mu within 4 with 99% confidence is quite a bit larger than the required sample size to estimate mu within 4 with 95% confidence. A few notes to finish. This is typically used as a rough approximation. We don't necessarily run out and get exactly 1,753 observations, even though the formula told us that's what we need. Also, the desired margin of error may not be practical. We might not be able to get a sample size of 1,753. It might cost us too much money, it might cost us too much time, or it simply might not be possible. So sometimes we might have to adjust our study plans or even abandon them altogether based on this calculation. And note that the population standard deviation sigma is usually not known, but we may have an estimate of it to use as a rough approximation in the formula. We may have done some previous studies and found out that the standard deviation is close to 50, and so then we might use 50 in the formula. We know that that's not exactly the case, but it gives us a rough approximation of the sample size that is required.